Have you ever looked down at your feet and, really wondered what's happening miles and miles beneath them? Our planet seems like this simple, solid sphere, but if you could slice it open.
Wow. Oh yeah, you'd find these distinct dynamic layers, constantly interacting, constantly shaping everything we actually see on the surface.
So that's what we're doing today, right? Taking a deep dive into that hidden world inside Earth.
That's the mission. We want to uncover how our planet got this incredible layered structure in the first place and explore the honestly ingenious ways scientists managed to see deep inside using some really powerful tools.
And understand what keeps Earth so alive
Uh,
compared to other planets, maybe.
exactly. What keeps it a living, breathing, churning system rather than just, a dead, lifeless cinder floating out there in space. And we'll connect it all back to things you see and experience like volcanoes or even the magnetic field that protects us all.
Okay, so let's start at the beginning. Earth now looks so organized, layers all neat. But you mentioned it wasn't always like that. The young planet, a hot mess, basically.
Huh, yeah. Hot mess is a pretty good description. I mean, imagine Earth's violent birth. Constant, high-velocity impacts from all the debris flying around in the early solar system.
Like cosmic bombardment.
Totally. Plus, you had the decay of these extremely short-lived radioactive elements inside the planet itself. Think of them like ancient internal mini-reactors. They gave off this powerful burst of heat right at the start.
Okay, so impact energy and radioactivity making it incredibly hot.
Hot enough to melt pretty much everything. The whole planet became hot enough for iron and nickel, the heavier stuff, to actually melt.
Melted, so a giant churning ball of molten rock and metal. How did that separate into the nice, neat layers we talk about today?
Well, that's where gravity steps in,
Hmm.
our cosmic sorting mechanism.
Hmm.
Picture this.
Hmm.
If you shake up a bottle of, say, muddy water with some iron filings in it,
Hmm.
and then just let it sit, what happens?
Right, the densest stuff, the iron filings, they'd sink straight to the bottom, then the mud, then the water, air on top, simple separation.
Precisely.
Yeah.
Perfect everyday illustration. And that's basically what happened on early Earth, just on a planetary scale. Those dense liquid metals, mostly iron and nickel, they sank gravitationally towards the center,
Forming the core.
forming the iron-rich core, exactly. And at the same time, the less dense molten rock sort of floated upwards towards the surface. It cooled and solidified to form the primitive crust.
So this whole process, this chemical segregation or differentiation, you called it.
Yeah, that established our three basic divisions.
Yeah.
The dense iron-rich core at the center, the thin primitive crust on the outside, and then the biggest layer, the mantle, sandwiched right in between. Earth basically sorted itself out.
That's a fantastic image, gravity just pulling everything into place. But I'm curious about the rocks themselves. As you go deeper under all that, incredible pressure, do they just get squeezed or do they fundamentally change?
Oh, they absolutely change. It's a great question. Density increases significantly with depth, right?
Mhm.
And part of that is compression, like squeezing a sponge. But a big part is also these fascinating phase changes.
Phase changes. What does that mean for a rock?
Well, take a common mantle mineral called olivine. At depths between, say, 300 and 400 kilometers, the pressure gets so intense that the atoms in the olivine crystal actually rearrange themselves. They form a new, denser, more stable crystalline structure. It's not a change in the chemical makeup, just a physical repacking. Same stuff, smaller box.
Okay, so these atomic rearrangements deep down, they're not just geological trivia, are they?
Hmm.
Do they connect to bigger things like volcanoes or even life?
Absolutely. They're fundamental. These dynamic internal motions, including those driven partly by phase changes and density shifts, are the very reason we have volcanism. This internal churning carries water and gases from deep within the Earth up to the surface.
Replenishing the oceans and atmosphere.
Exactly. So in a very real sense, Earth is alive from the inside out. It's constantly renewing itself in ways that are absolutely fundamental for life to exist on the surface. Without this internal engine, our planet would look vastly different, likely barren.
That really drives home how connected everything is. Now, obviously, we can't just, dig a hole to the center of the Earth. I think the deepest hole is only about 12 kilometers, right? Barely scratching the surface.
Not even close, yeah. 12.3 kilometers, the Kola super deep borehole. It's amazing, but compared to Earth's radius, it's nothing.
So how do we know what's down there? How do we map these incredible hidden layers thousands of kilometers beneath us?
This is where geology gets really clever. We use seismic waves, the waves generated by earthquakes. They're essentially Earth's natural medical X-rays.
Earthquakes as X-rays. Okay.
Think about it. There's something like 3,000 earthquakes every year, strong enough for their waves to travel all the way through the Earth.
Yeah.
And we have seismograph in the unseeable.
Right, so earthquakes happen, waves travel through, but how does that tell us if something 3,000 kilometers down is liquid or solid, or what it's made of? What's the trick?
It boils down to how the waves travel. The speed of seismic waves, we mainly look at P waves, primary waves, and S waves, secondary waves, depends critically on the properties of the material they're moving through.
Properties like,
Things like stiffness, compressibility, temperature. For instance, P waves slow down quite a bit when they hit molten or partially molten rock. And crucially, S waves are secondary. Shear waves cannot travel through liquids at all.
okay, so if S waves just disappear at a certain depth,
Bingo. You know you've hit a liquid layer. That's a huge clue right there.
and it's not just about speed, is it? Don't they bounce off things?
They do. When seismic waves encounter a boundary between different materials, like the boundary between the mantle and the core, they behave in predictable ways. They can undergo reflection, basically bouncing off like an echo,
Okay.
or they can experience refraction. That's where they bend as they pass from one material into another, kind of like how light bends when it goes from air into water.
Right, like a straw in a glass looking bent.
Exactly that principle. And waves also naturally follow curved paths as they go deeper, just because the rock generally gets more compact and rigid, which speeds them up slightly and causes them to curve back towards the surface eventually.
So it's like an incredibly detailed ultrasound for the planet. We're mapping boundaries, density changes, by tracking how these waves speed up, slow down, bounce, and bend.
Precisely. And it's not just one earthquake or one path. We use signals from thousands of earthquakes, recorded by a global network of seismographs. Sophisticated computer algorithms process all this data, comparing arrival times and wave shapes.
Allowing you to build up a 3D picture.
Exactly. These wave behaviors, their speeds, reflections, refractions, the shadow zones where they don't appear, have been absolutely crucial. They've allowed us to identify the distinct boundaries and layers within our planet, giving us this incredibly detailed map of what lies beneath our feet.
Okay, so we know how we see inside. Let's actually take that dive now, layer by layer. Starting right here, our home base, the crust. What makes it tick?
Right, the crust. It's Earth's relatively thin, rocky outer skin. But even though it's thin, it's incredibly diverse. We essentially have two main types.
Oceanic and continental.
You got it. Oceanic crust is what makes up the ocean floors. It's typically only about 7 kilometers thick. It's constantly being formed at mid-ocean ridges, so it's relatively young. Geologically speaking, usually 180 million years old or less.
And it's denser stuff.
Yeah, denser. Around 3.0 grams per cubic centimeter, mostly composed of dark igneous rocks like basalt and gabbro.
Okay, then what about continental crust, the stuff we live on?
That's quite different. It's much thicker, averaging around 40 kilometers, but it can bulge up to 70 kilometers thick under major mountain ranges like the Himalayas.
Wow. And it's made of different rocks.
Many different rock types, yeah.
Yeah.
The average composition is something like granodiorite, think granite-like rocks.
Yeah.
It's also much, much older. We've found continental crust rocks that are over 4 billion years old.
4 billion, that's incredible.
It really is. And crucially, it's less dense than oceanic crust, only about 2.7 grams per cubic centimeter. This lower density is key. It's why continents are buoyant. They essentially float higher on the mantle, like giant rafts.
Rafts, I like that. So how did scientists figure out exactly where the crust stops and the next layer, the mantle, begins? Is there a sharp line?
There is a surprisingly sharp boundary called the Moho. That's short for the Mohorovic discontinuity.
Catchy name.
Ah, yeah. It was discovered way back in 1909 by a Croatian seismologist, Andrija Mohorovic. He noticed something odd in seismic wave data. P waves suddenly sped up.
Sped up? How much?
Quite a jump. From about 6 kilometers per second in the lower crust to around 8 kilometers per second just below it. That sharp increase signals a change in material, the boundary between the crust and the upper mantle.
How did he use that speed difference?
He realized that for earthquakes farther away, waves that dipped down into this faster mantle layer refracted back up and then traveled to the seismograph actually arrived sooner than the waves that traveled directly through the slower crust. It's like choosing the interstate. Versus local roads, the interstate's faster, even if the route is slightly longer.
So by finding that crossover distance where the refracted wave arrives first, he could calculate the depth to that faster layer, the Moho?
Exactly. And we find the Moho is much deeper under continents, maybe 25 to 70 kilometers down, compared to only about 7 kilometers beneath the ocean floor.
Okay, so below the Moho, we enter the mantle. Earth's biggest layer, you said.
By far, it's immense. Nearly 2,900 kilometers thick. makes up over 82% of Earth's total volume.
And what's it like? Is it molten?
Mostly solid, actually.
Yep.
It's a solid rocky layer composed mainly of silicate minerals rich in iron and magnesium. We have samples like peridotite xenoliths that get brought up in volcanic eruptions, giving us a direct look. But here's the fascinating part.
It can flow.
Yes, even though it's solid rock, it's so hot and under such immense pressure that over long geologic timescales, millions of years, it behaves like a very, very viscous fluid. Can flow or convect. Think of something like asphalt on a hot day, or maybe cold honey. It moves.
Wow. So this massive mantle, is it all uniform?
Not quite. We subdivide it further, especially the upper part. The very top bit of the mantle is strong and rigid, and it's fused with the crust. Together, they form the lithosphere. That's the rigid outer shell that makes up tectonic plates.
The plates that move around.
All right. Beneath the lithosphere is the astenosphere. This is a weaker, hotter layer. It's still mostly solid, but it's close enough to its melting point that it's much less rigid and capable of that slow flow we talked about. The lithosphere basically slides around on top of the asthenosphere.
Got it. And deeper still.
Below the asthenosphere, between about 410 and 660 kilometers down, we hit the transition zone. This is where those phase changes really kick in. Intense pressure forces minerals like olivine to collapse into denser structures, like ringwoodite and wadsleyite.
More atomic rearranging.
Yep. And below 660 kilometers, we're in the lower mantle. This extends all the way down to about 2,900 kilometers. It's mostly made of an extremely dense mineral called perovskite, now officially named bridgemanite. This lower mantle alone is Earth's single largest layer, making up 56% of the planet's entire volume.
Incredible scale. Is there anything else between the mantle and the core?
There is a really weird and complex layer right at the bottom of the mantle, the lowest few hundred kilometers. It's called the DOA layer, D double prime.
D double prime. Why the strange name?
It's historical from early seismic models, but it's a fascinating place. It's highly variable, directly in contact with the liquid outer core. It's thought to be kind of a graveyard for subducted oceanic lithosphere, old, cold tectonic plates that have sunk all the way down.
Wow. And does anything come up from there?
We think so. It might also be the birthplace of deep mantle plumes, columns of unusually hot rock that rise up towards the surface, potentially feeding hotspots like Hawaii or Iceland. There's even evidence from seismic waves slowing down that parts of the D layer might be partially molten. It's a really dynamic boundary zone.
So much going on down there. How was this super deep boundary between the mantle and the core first figured out?
That discovery goes back to 1906 to Richard Dixon Oldham. He noticed these shadow zones on the opposite side of the Earth from an earthquake.
Shadow zones, like places the waves couldn't reach.
Exactly. He observed areas where P waves were either absent or arrived much later than expected, and areas where S waves didn't arrive at all. He correctly deduced that there must be a large central core that was blocking or drastically bending the waves. The liquid outer core, especially, creates a large shadow where S waves just can't penetrate.
Amazing deduction from shadows. Okay, let's finally go there to the very heart of our planet, the core. What's it made of?
We think the core is primarily an iron-nickel alloy, probably with some minor amounts of lighter elements mixed in, like oxygen, silicon, maybe some sulfur.
And it's dense, right? You mentioned that earlier.
Extremely dense. It only accounts for about 1/6 of Earth's total volume, but it makes up a full third of its mass. The density is over 10 grams per cubic centimeter, climbing up to maybe 13 gc-meter right at the center. Way denser than anything at the surface.
And the core itself has parts too, doesn't it?
It does. Two distinct parts. The outer core is a thick layer, about 2,270 kilometers thick, and it's liquid-A.
Liquid metal deep inside the Earth. How do we know for sure it's liquid?
That goes back to the S waves. They simply cannot travel through the outer core.
Yeah.
That inability of shear waves to pass through is definitive proof it's liquid.
And this liquid layer is important?
Hugely important. The vigorous movement, the convection of this electrically conductive liquid iron in the outer core is what generates Earth's magnetic field. It's our planetary dynamo.
Okay, so liquid outer core, then what's at the very center?
At the very center lies the inner core. This is a solid sphere with a radius of about 1,216 kilometers.
Solid, but isn't it even hotter down there?
It is hotter, yes. Hotter than the outer core. But the pressure is also absolutely immense. Millions of times atmospheric pressure. This incredible pressure raises the melting point of iron above the actual temperature, forcing it to be solid despite the heat.
pressure freezing it solid, that's counterintuitive.
It is, and this solid inner core is actually growing slowly over geologic time as the Earth gradually cools and more iron crystallizes out from the liquid outer core.
Wow. Now, I heard something really wild about the inner core. Something about how it moves.
Ah, you heard right. This is one of the most mind-bending discoveries. Seismic studies suggest the solid inner core actually rotates independently from the rest of the Earth. And not just independently, but slightly faster.
Faster, so it's like lapping the mantle and crust.
Essentially, yeah. It seems to gain about a degree of longitude per year relative to the surface, maybe lapping the rest of the planet every few hundred years. Imagine a solid ball spinning inside a liquid shell, doing its own thing.
That is absolutely incredible. A planet within a planet.
And it might be even more complex. Recent studies analyzing subtle seismic wave paths suggest there might even be an inner core, a distinct region right at the center, maybe with iron crystals aligned differently than in the layer just outside it.
Wow. Okay, how was this boundary discovered? The one between the liquid outer core and the solid inner core.
That discovery belongs to the Danish seismologist Inge Lehmann back in 1936. She noticed faint P waves showing up in the P wave shadow zone places they shouldn't have been if the core was entirely liquid. She hypothesized they were reflecting off or refracting through a solid inner core with a higher velocity. And she was right.
So many layers, different states, phase changes, independent rotation. What keeps this whole incredible structure so dynamic? What's the engine driving all this churning and movement?
In a word, heat. It's all about the flow of heat. Earth's center is incredibly hot, around 5,500 degrees Celsius, about as hot as the surface of the sun. The surface, meanwhile, averages a cool 15 degrees C.
That's a massive temperature difference.
Huge. And heat naturally flows from hot to cold. So there's this constant, relentless outward flow of heat from the deep interior towards the surface, trying to escape into space. That flow is what drives almost all the internal processes we've discussed.
Where did all that heat come from originally? And what keeps it going after 4.5 billion years?
Good question. Earth's thermal history really has two main stages. The first was early heating. Right at the beginning, during formation, you had all that energy from planetesimal collisions, kinetic energy, converting into thermal energy.
The impacts we talked about.
Right. Plus, the decay of those short-lived radioactive isotopes, like aluminum-26, pumped a lot of heat into the young Earth. And the giant impact that formed the moon likely melted the core and mantle again. So early Earth got very hot very quickly.
Okay, but that heat should have dissipated over billions of years, shouldn't it?
It should have, and Earth has been cooling gradually. But it hasn't frozen solid thanks to the second stage, a slave burner effect. The mantle and crust contain long-lived radioactive isotopes, things like uranium-235, uranium-238, thorium-232, and potassium-40.
The kind used in nuclear reactors.
Some of them, yeah. They decay very slowly, releasing heat over billions of years. This radiogenic heat is constantly being generated within the Earth, replenishing the heat supply. It's this ongoing heat production that continues to drive mantle convection and, ultimately, plate tectonics today.
So it's like Earth has its own internal, slow-burning nuclear furnace keeping things warm.
That's a pretty good analogy, yeah.
Okay, so we have this heat flowing outwards. How does it actually move through the different layers? Is it like heat traveling through a metal bar?
That's one way, called conduction. It's the transfer of heat through direct atomic collisions or electron flow. It's pretty efficient in metal, so it's important in the core. It also happens in the rigid lithosphere and maybe the DO layer. But rocks, generally, are poor conductors of heat, like insulators.
So conduction isn't the main way heat moves through the huge mantle.
No, not through most of it.
Yeah.
The dominant mechanism for heat transfer within Earth's interior, both the mantle and the liquid outer core, is convection.
Convection, like boiling water.
Exactly like boiling water. Hot, less dense material at the bottom gets buoyant and rises. As it reaches the top, it cools, becomes denser, and sinks back down. This continuous circulation, this overturning, is incredibly efficient at transporting heat.
And that requires the material to be able to flow, right? Even if it's solid rock flowing slowly.
Absolutely. Convection requires thermal expansion. Heating makes it less dense. Gravity-induced buoyancy, less dense stuff floats. And enough fluidity even if it's incredibly slow, like mantle rock viscosity.
You mentioned convection in the outer core, too, driving the magnetic field. Is there anything special about that?
There is. Besides the normal thermal convection, there's also chemical convection happening in the outer core. As the solid inner core grows, it crystallizes out nearly pure iron. What's left behind in the liquid outer core is slightly enriched in lighter elements, making it less dense and more buoyant.
Ah, So as the inner core freezes, the leftover liquid floats upwards.
Precisely. This chemical buoyancy adds another powerful driving force to the convection in the outer core, helping to vigorously stir that liquid iron and generate our magnetic field. It's a combined thermal and chemical engine.
What about radiation? Does that play a role inside the Earth?
Not really within the interior. Radiation is how heat travels as electromagnetic waves, like heat from the sun reaching Earth. It's the primary way Earth loses heat from its surface out into space, but it's not significant for moving heat through the dense rock and metal inside.
Okay, so mostly convection in the mantle and outer core, some conduction. How does the actual temperature change as you go deeper? Is it a smooth increase?
Not entirely smooth. We describe it with a geothermal gradient, or geotherm. It increases quite rapidly in the crust, maybe 20 to 30 degrees Celsius per kilometer near the
That's
surface.
pretty steep.
Yeah, but then it slows down dramatically through most of the mantle, increasing only about zero point 0.3 degrees Celsius per kilometer. The convection is efficiently moving heat, so the temperature gradient is much shallower.
Okay.
But then, in that DO layer at the base of the mantle, it steepens again, increasing by maybe over 1,000 degrees C across that relatively thin zone, and the core itself ranges from around 4,000 degrees C at the top of the outer core to that estimated 5,500 degrees C at the center.
And how does this temperature profile relate to whether a layer is solid or liquid?
That's the crucial connection. You have to compare the actual temperature, the geotherm, with the melting point of the material at that specific depth. And remember, the melting point also increases with pressure.
Right, pressure makes it harder to melt.
Exactly. So in the outer core, the actual temperature is higher than the melting point of iron at that pressure. Hence, it's liquid.
Mhm.
But in the inner core, even though the temperature is even higher, the pressure is so immense that it raises the melting point above the actual temperature, so it stays solid.
I see. And this also explains why some layers are weak, like the asthenosphere.
Precisely. In the asthenosphere, the temperature is very close to the melting point. The rock isn't fully molten, but it's hot and weak enough to deform and flow easily, allowing the rigid lithosphere to slide over it. Similarly, the DO layer might be partially molten in places because it's heated from below by the core. This interplay between the geotherm and the melting curve dictates the physical state, solid, liquid, strong, weak of each layer.
Understanding that heat flow really connects everything, from plate tectonics to volcanoes and earthquakes, it's the engine driving it all.
It really is. And it dictates the long-term evolution of the planet.
So we've painted this picture of layers, heat flow, but you mentioned earlier it's not perfectly neat. Like an onion, there are variations within these layers.
Oh, absolutely. Earth isn't perfectly spherically symmetric inside. Geophysical methods show significant horizontal variations, differences side to side, not just top to bottom. These are directly tied to mantle convection and plate tectonics.
Okay, how do we detect those? Let's start with gravity. I always
Uh,
thought gravity was the same everywhere on Earth, more or less. Is it?
Not quite. First off, Earth isn't a perfect sphere.
Right.
Because it rotates, it bulges slightly at the equator, and is flattened at the poles. It's an oblate ellipsoid. This means you're slightly farther from the center at the equator, so gravity is actually a tiny bit weaker there. Your measured weight is about 0.5% less at the equator than at the poles.
Didn't know that. But are there other variations?
Yes, gravity anomalies. These are variations from the expected gravity value once you account for latitude and elevation. They tell us about density differences underground. A positive anomaly, stronger gravity than expected, suggests denser rock beneath the surface.
Like maybe a rich ore deposit?
Or large intrusions of dense volcanic rock, like under the mid-continent rift in North America. Conversely, a negative anomaly, weaker gravity, suggests less dense material, like the thick accumulations of low-density sediments in a basin or the hot, stretched, less dense crust in the Basin and Range province of the western U.S.
Can we see bigger patterns related to the mantle?
We can, especially with sensitive satellite gravity measurements. These reveal large-scale anomalies that seem linked to mantle convection, broad areas of slightly lower gravity over mantle upwellings, hot plumes, and higher gravity over downwellings, cold, sinking slabs. Gravity gives us a window into deep-density structures.
Okay, gravity shows density variations, but can we get a more direct 3D image, like a CT scan of the Earth's insides?
That's exactly what seismic tomography provides. It's very similar in principle to medical CT scanning. Instead of X-rays, we use seismic waves from thousands of earthquakes, recorded by hundreds or thousands of seismographs all around the world.
How does that create an image?
By carefully measuring the travel times of P and S waves along many crossing paths through the mantle. If waves consistently arrive faster than average through a certain region, it implies that region is colder and denser than its surroundings. If they arrive slower, it implies the region is hotter and less dense, or perhaps partially molten.
And you map these out.
Yes, computer algorithms reconstruct these velocity variations into 3D images. Typically, faster than average regions, cold, dense, are colored blue on tomographic maps, while slower than average regions, hot, less dense, are colored red.
So this isn't just confirming the layers, it's showing the dynamic churning within them. What kind of things do these scans reveal?
They reveal incredible structures. We can clearly see the cold, thick keels of ancient continental lithosphere extending deep beneath continents like North America and Africa, blue areas. We see the hot, slow upwellings beneath mid-ocean ridges like the Mid-Atlantic Ridge, red area.
Can you actually see plates sinking?
Absolutely. Some of the most striking images show vast slabs of cold, subducted oceanic lithosphere plunging deep into the mantle, sometimes appearing to stall at the 660-kilometer transition zone, other times sinking all the way to the core mantle boundary. We can literally track the graveyard of ancient tectonic plates, like the Farallon plate beneath North America.
And the plumes coming up from the D's layer.
Yes. Tomography provides strong evidence for massive upwelling structures, sometimes called superplumes, rising from the core mantle boundary, particularly beneath Africa and the Pacific. These might be the source of mantle plumes that feed hotspots. It's truly visualizing Earth's internal engine at work.
That's amazing seeing the convection currents. This brings us to one of Earth's most vital features, generated by all this motion deep down, the magnetic field. How exactly does that work?
Right. Earth's magnetic field, generated by the geodynamo, comes back to that vigorous convection in the liquid iron outer core. Because iron is a metal, it conducts electricity, and its motion generates electrical currents.
Like in an electric generator.
Exactly. As this electrically charged fluid moves and convex, Earth's rotation organizes the flow, twisting it into spiraling columns roughly aligned with the rotation axis. This complex motion acts like a giant self-sustaining electromagnet, producing the magnetic field we observe, which is mostly dipolar, meaning it has a north and south magnetic pole, like a bar magnet.
But it's not perfectly stable, is it? I heard the magnetic poles move.
They do. It's a very dynamic system. The magnetic poles wander over time. For example, the north magnetic pole has been drifting quite rapidly northwestwards in recent decades, currently moving at over 70 kilometers per year.
Wow. And sometimes they flip entirely.
Yes, magnetic reversals.
Yeah.
At seemingly random intervals, typically thousands to millions of years apart, Earth's magnetic field weakens significantly, the poles wander erratically, sometimes even crossing the equator, and then the field reestablishes itself with the opposite polarity. North becomes south, and south becomes north.
So a compass would point south?
During a reversed period, yes. The evidence for these reversals, recorded in the magnetism of ancient rocks, particularly on the ocean floor, was actually fundamental proof for the theory of plate tectonics and seafloor spreading.
And this field is crucial for us on the surface, isn't it?
Absolutely vital. The magnetic field extends out into space, creating the magnetosphere, which acts like a shield. It deflects most of the harmful charged particles constantly streaming from the sun, the solar wind. Without it, the solar wind could strip away our atmosphere and bombard the surface with dangerous radiation.
So a weakening during a reversal could be bad news.
It could potentially increase radiation exposure at the surface, which might pose health hazards for life. The magnetosphere is our planetary force field, and the geodynamo in the outer core keeps it powered up.
It's just incredible how these deep Earth processes, convection, phase changes, the geodynamo, are all interconnected and shape our world. What's the big picture takeaway from understanding all this internal complexity?
I think the main takeaway is that Earth is a truly dynamic system. The layers aren't static, they're constantly interacting, driven by heat flow and convection. Their motions are profoundly interconnected, often in complex ways, and sometimes occurring in pulses or cycles.
Can you give an example of that interconnection?
Sure. Think about the breakup of the supercontinent Pangaea. Following its breakup, there was a long period, maybe 80 million years, of increased subduction, more cold oceanic plates sinking into the mantle. Some studies suggest this pulse of cold material reaching the core mantle boundary actually chilled the top of the outer core.
And that affected the magnetic field.
It seems so. That chilling effect might have led to more vigorous convection in the outer core, which, perhaps counterintuitively, stabilized the magnetic field and prevented any magnetic reversals for a long stretch of about 35 million years. During the Cretaceous period, the Cretaceous normal superchron.
Wow. So sinking plates affected the core and the magnetic field.
And at the same time, displacing all that cold material downwards likely caused hot mantle material to rise elsewhere. possibly contributing to the formation of large mantle plumes and massive volcanic eruptions known as flood basalts during that same period. It's a perfect example of how events are linked across different layers and systems. Earth is this complex, churning, pulsing planet.
What a journey we've taken. From the fiery, messy birth of our planet, sorting itself out into layers.
To using the subtle whispers of earthquake waves to map those layers thousands of kilometers down.
Through the distinct crust, the vast flowing mantle, the enigmatic D's layer, and into the liquid outer and solid inner core.
Exploring the heat engine that drives it all, the convection currents we can now visualize with tomography, and the magnetic shield generated deep within.
It really shows how our planet is far from just a static ball of rock. It's dynamic, constantly evolving.
And the processes hidden deep beneath our feet are directly shaping the surface we inhabit, building mountains, driving volcanoes, creating oceans, providing the air we breathe, and maintaining that protective magnetic shield.
Truly alive from the inside out. It leaves you wondering.
What might these deep Earth processes reveal next? What secrets does the future hold for our planet's evolution, or even for life itself, as this complex engine continues its endless, churning work over the millennia to come?
A lot to think about. We hope you enjoyed this deep dive with us into Earth's interior. Until next time, keep exploring.